Hello, everyone. Welcome to this webinar on simulation-driven design and optimization of a KSB heat circulator pump using CAESES and SimScale. I'm Kanchan, Product Manager for Rotating Machinery at SimScale, and I'm one of the presenters for today's webinar. Also joining me as co-presenters are Matthias Brenner from Friendship Systems and Tony Klemm from KSB Germany. Before we proceed, I'd like to give you all a quick reminder that your mics will remain on mute during the course of the webinar. Should you have any questions, please feel free to reach out to our support staff using the live chat option. So let me start by properly introducing all your presenters, starting with myself. I am an aerospace engineer by training, and over the last 10 years, I have had extensive experience in developing CFD software for helicopters, wind turbines, and propellers. And now at SimScale, I'm driving the development and promotion of SimScale's technology for the turbomachinery and rotating equipment industries. I'm really excited to be part of this webinar and look forward to a really good presentation. My co-presenter, Matthias Brenner, is the head of sales at Friendship Systems. With a background in naval architecture, Matthias has 13 plus years of experience in working with different industries, ranging from marine, energy, and transport, both on the sales and engineering sides. And today he is here to share his expertise and his wide experience in creating customized workflows for pump design and optimization. Matthias, we are very excited to have you here with us. Thank you for joining.
Thank you very much, Kanchan. I'm very excited to be here as well, and welcome to all our attendees from my side as well.
My second co-presenter is Tony Klemm from KSB Germany. Tony has had a classical mechanical engineering education with a heavy focus on fluid dynamics and turbomachinery, and he's currently working as a CFD application and design engineer at KSB. He brings with him nearly 16 plus years of industrial experience in hydraulic equipment and pump design. Tony, thank you so much, first of all, for making this project possible and for joining us today to talk about it in this webinar.
Thank you for introduction and welcome to all attendants.
Thanks, Tony, and thanks, Matthias. So without further ado, let's dive into the agenda for today's webinar. I'll begin with giving a brief overview of SimScale as a company and our offering for the turbomachinery industry to see how it can make a difference to your own design and simulation workflow. I'll also touch upon the SimScale API that made it possible to integrate SimScale with CAESES for undertaking the current project. Tony will then share with us the specific objectives of the project, on why we embarked on this project for designing and optimizing a circulator pump impeller. This will help us understand the industrial use case. And last but definitely not the least, Matthias will go into details of the CAESES SimScale API-based workflow and how it was used to develop a surrogate model for the pump impeller. So here's a quick overview of SimScale as a company. We were founded in 2012 with the vision of democratizing simulation and making it accessible to engineers everywhere. Today, we have over 400,000 users worldwide, spread across maybe 50 plus countries and many time zones. And I'm happy to say that we are adding more users every day. Our vision for democratizing simulation means that we ultimately want to empower every engineer to innovate faster. And we achieve this by breaking down the technical barriers around software and hardware investment and simulation know-how. Because SimScale is completely browser-based, our software and hardware footprint is essentially zero. Plus, in order for simulation to be actually accessible, it also has to be affordable, economical. We understand that. And for this, we offer cost-effective usage-based licensing, which means you as a user or the company as a customer doesn't have to worry about optimizing simulation use subject to node-based licensing or available compute resources, which is like virtually unlimited when you are on the cloud. So this way, our customers are able to leverage simulation early in the design process and throughout the product lifecycle, across projects, across teams in a very collaborative manner. So what are the specific features that set us apart from on-premise software? Firstly, there is no installation or version control required. All you need is a decent internet connection with a web browser. So you just have an account and you sign up and you start simulating. And through this one web-based login, you have access to a wide range of high-end physics across fluids, structural, and thermal analysis. And you can also leverage our open API structure to couple simulation with your own design and PLM tools, which is the topic of today's webinar, as you will see shortly. I also want to give you a brief technical overview of the SimScale's CFD solver for turbomachinery, because this is the solver that has been used for running the simulations in the current project. It has tailored methods and heavy UI automation for turbomachinery applications. Most importantly, it is industry validated for high accuracy, and the cloud-native architecture means that it is possible to obtain pump curves in literally minutes. And as a testimony, that is what you see on the screen in the middle with the centrifugal pump validation, where you see a transient simulation for a pump curve with 3 operating points that was run in just 15 minutes. We also offer multidisciplinary analysis for turbomachinery and related equipment within SimScale through the same login. So you can basically, bring in one CAD model of a pump or a motor, run CFD simulations to obtain your performance curve, do a stress test or a thermal evaluation, and do vibrational analysis to obtain your Campbell diagram. So all of this multiphysics analysis is possible within the same platform. And our development focus is heavily on providing in-platform parameterization of design to enable fast design iterations. At the same time, we are also investing heavily on high-end physics at the backend so that there is no compromise on accuracy. We are creating automated workflows specifically for turbomachinery, which includes API support for easy integration with design and PLM tools. Which brings me to the topic of the SimScale API exactly. How does it look like? It's quite simple, to be honest. It is based on the REST architectural style. And while we support programming in many languages, we provide specific software development kits in Python and C#. And all the compute, storage, and licensing details are taken care of by SimScale. And a simple programmatic access is provided to couple or integrate SimScale or simulation in SimScale with CAD design tools, PLM software, 1D codes, 2D codes, you name it. And that's what you see in the slide here, the different use cases for SimScale's API. Through the programmatic interface, you can integrate cloud-native simulation into early-stage design exploration, maybe predictive maintenance, 1D, 3D co-simulation, or design validation for compliance purposes. For example, in the current project, the SimScale API is used to automate CFD simulations, thus launching a DOE involving hundreds of design variants of a heat pump, and then make design decisions based off of the CFD results. So this is an overview of the workflow, and this has been achieved by coupling the CFD solver, the turbomachinery solver, which I talked about a couple of slides before, with Friendship Systems KSB's software, which is used for CAD design and optimization. But before we deep dive into understanding the exact workflow and the project outcome, let's hear from Tony about the project objectives from a real-world industry perspective, because I believe this will help us understand how digital prototyping can make a difference in developing better designs and reducing the cost of physical production. I will now hand over to Tony.
Thank you, Kanchan. Okay, my part now is to tell you something more about the background of the project. Today here I will start with a marketing slide, and which shows you a typical product portfolio of such KSB circulator pumps. What you also can see is a label which is called ERP, which means energy related products, and this or behind this is a directive of the European Union to save energy, especially regarding pump application. And the main criteria of this directive is the so-called EEI. You see it here on the screen. On the slide, there are the EEI, Energy Efficiency Index, is named here sometimes, and it's important to sell this product. So that means if you want to sell a product or a pump, especially this pump, the energy efficiency index must be low a certain value. This is 0.23 in this case for heating pumps. Yeah, and yeah, the energy efficiency index is a little bit complicated to explain, and that's why here I will have a slide to explain you this a little bit more. The energy efficiency index is defined by the ratio of an average power consumption at 4 different weighted flow rates and on an hydraulic reference power. Different flow rates means 100% flow rate, 75%, 50%, and 25% flow rate, and then the specific electrical power at this point. The 100% point is defined here at a maximum hydraulic power, which means at this 100% point, the flow rate is exactly the same where the flow rate, where the hydraulic power is maximal. Okay, and now I want to explain you this a little bit more. And on the right hand side here, you can see a typically characteristics curve for head for this pump, and you see here the curve for maximum speed. And in this diagram now we can prescribe the flow rates. The flow rates at 100% point, we already defined this at maximum power, and we need still the flow rate, or we need still the flow rate 0. And the flow rate 0 is defined if, or the head for flow rate 0 is defined by the half of the 100% head of this pump. And what does it mean now? Now we have to go further in this diagram, and now we can point out the flow rate of 75% with a new speed, because maybe I forgot to mention these pumps are completely speed controlled. Yeah, and we can going on and to set up the next two flow rates, and then we have our four flow rates defined at different speeds of the pump and at different operating points, especially regarding of the characteristic curve, if it's part load or overload maybe. Yeah, the pump is not running in the best efficiency point anymore. Okay, now and then sometimes can happen, or most of the time, yeah, depends on the pump. The motor power is limited. That means the 100% point here moves to a lower flow rate, and that means also all other points are changing, and so also the energy efficiency index is changed. And this means for an optimal impeller regarding a low EEI depends also on the motor characteristics and on the power consumption at part load. Yeah, this is the main point here. It's a very open system. Yeah, and one thing to mention is that the weighting for the flow rate, for the low flow rate of 25% is the highest. Yeah, that means part load here in this case is taken into account for this energy efficiency index. Okay, now to the main motivation here. In pump industry, often the motor or system components are varying until a far progressed product development phase. And that means impeller selection has to be done fast and reliably at the end of the product development process. And everybody knows here, I think, who is attending in this webinar, we need a simulation-driven design process. Yeah, but we have some problems here. The problems are the calculation of the EI depends on measured curves. Yeah, this is one thing. Then to reduce the computational efforts, pump performance is generated by steady-state impeller only CFD simulations. And this results in differences between measured and calculated pump head curve. You see it here exemplarily on the right-hand side. Yeah, the gray area. This is a missing information because CFD calculation gives us only the theoretical head of the pump. Yeah, and solution for this is we need to calculate the EI with approximated performance values. And yes, the approximation of the measured head curve will be done by application of different assumptions on the calculated curve. Yeah, and what does it mean? Of course, we have a lot of things to do, and so we need a tool chain, and we want to develop here a tool chain to get the EI by simulation-driven processes. And yeah, this is a point where I need to hand over to Matthias, who will show us the hydraulic simulation concept a little bit more in detail. Okay.
Excellent. Thank you very much, Tony. So I'm going to take over. Yeah, so I will talk about the workflow that we created or try to develop for this hydraulic design part of the circulator pump. And let me see. Okay. So the motivation, as we've seen from Tony, is this so-called energy efficiency index. We want to design pumps that have a low energy efficiency index, and our aim is to develop the hydraulic part of the tool chain with the target to minimize this energy efficiency index of the pump. And the idea that we followed in the work we did in this project was to do or facilitate the pump selection using a surrogate model, and that surrogate model is generated by impeller CFD simulations. That's, so to say, the concept that we're trying to follow. And different steps that we did were, first of all, we need to start with modeling of a parametric impeller, so that we have a geometric representation of the impeller that we can easily change and vary. The next step is then to connect this geometry representation to SimScale to allow computing it and analyzing the performance. Once we have that connection in place, we can run a DOE, which means design of experiments, so a systematic parameter study of the impeller, changing all kinds of different properties of the geometry. And then with the data that we have obtained by computing all these different impeller variants, we can generate a surrogate model or multiple surrogate models. And with these surrogate models, we can then run an optimization on the impeller geometry. Okay, before we get into these steps, let me just very briefly talk about KSB, because I'm sure several people who join here today are not familiar with what we do and what our tool is. So the target of what we're doing here at Friendship Systems and with our tool KSB is automation of the design process, or at least of parts of the design process. And the reason is that there is laws and regulations, as we see here with the energy efficiency index, as well as competition on the market, so that the products that are being designed need to be performing very well. And we think these goals can only be reached with optimization. And this kind of automated optimization and design exploration processes, first of all, obviously lead to better and optimized designs, but they also shorten the development times and reduce the design cycles that are necessary to get to a certain goal. And finally, this is, I think, a very important point, they help to greatly increase the knowledge about the product behavior. So it means what are the influences on the performance of the product very early in the design process, where the freedom for making decisions is very large. And then we can use that information to make design decisions. And that will lead us to our final developed product. And to automate the design process, we basically need three components. We need a simulation tool that is able to provide the performance information that we're looking at. We need a driver of the optimization process, so basically an optimization tool that provides all the algorithms that we need for optimization or design of experiments and other things that are necessary within this process. And finally, we need a suitable CAD tool that is able to produce these different geometry variants that we want to analyze with the simulation. And these final 2 points or components that are needed in the automation of the process are what we provide with our tool cases. So finally, one thing to answer. So I think this is a commonly asked question if we mention, okay, CAESES is by a big part a CAD tool to generate different geometry variants. Why would I need another CAD tool or another CAD system? Obviously, most people that are doing engineering, if not all, are have access to some sort of CAD system. And the answer is that in our experience, when we want to set up these kind of automated processes, most of the bottlenecks that people encounter are related to the handling of the geometry. So typical things that might happen is that geometry variation with a traditional, I call it here, let's say normal mechanical CAD system is often difficult. People encounter a high failure rate. So if you change parameters of your geometry in an automated way, the system is not able to regenerate these geometries, so it breaks down, the model breaks down, or you get infeasible geometries. So that's a serious issue. Another important point are constraints. So when we're optimizing a geometry, we would like typically to fulfill certain constraints, maybe due to manufacturing, because you have a certain manufacturing process, or due to I don't know, the available space and so on. So it's important to make sure that the geometry at the end of the optimization process fulfills these constraints. So this is also something that is not always easy to do. Another issue is that simulation engineers might depend on another department, on the CAD department, to provide the geometry or geometry variants, and also that the quality of the CAD model as it comes out straight off the CAD might not be suitable for simulation. So that, of course, makes it difficult to automate things if manual work is necessary to clean up the model, for example. And basically, these are the things that the points that we're trying to address with CAESES. So CAESES is not a general purpose CAD tool, but a very specialized, highly specialized CAD tool with the specific intent or focus on geometry variation, especially of complex geometries where we typically have free-form surfaces and things like that, like you see here in these examples. All right, so now let's go to our actual project that we want to talk about and look at the different project steps. So the first thing is CAD modeling and the CAD variation. Basically, as I said, we created a parametric model of the pump impeller, and the steps that we go through to generate that model start by defining the meridional contours of the pump. So we have the hub contour, the shroud contour, and the leading and trailing edge of the blade. This is the first step. Then we can basically revolve the hub and shroud contour to generate these surfaces. And in the next step, this is very important, we can start generating the impeller blade by defining the mean camber surface. And the mean camber surface is defined by blade angle distributions. In this case, there is different approaches to do that, but in this case, we used blade angle distributions, which basically define how the angle of the blade is changing, going from the leading to the trailing edge of the blade. And in this case, we used 3 sections at the hub, at the shroud, and in the middle. And with these 3 curves, we can create the mean camber surface. And then in the next step, we apply thickness to the mean camber surface to also defined in a parametric way. And then we get our, so to say, our solid for the blade, which we can then intersect with hub and shroud. We can create fillets at the root and at the tip of the blade, and then we have basically our finalized impeller. In addition to that, in this case, we also generated the flow domain geometry for the CFD calculation, so it's slightly different than the final impeller solid, so to say here. This is the volume where our flow is happening and where we're running the CFD computation, and that is also generated here as part of the parametric model. So this is the model generation, and now, as I said, we want to be able to vary the geometry, create different variants of the impeller. So we defined a bunch of different design variables, which I will try to explain now. The first one, I think, is easy to explain. That's the number of blades. We allowed a variation of the number of blades between 4 and 7 here, as you can see in the animation. Then we had 3 different design variables or parameters that were assigned to the meridional contours. You can also see them in the animation here. So the first one, which is called D111 here, this is the outer diameter of the pump inlet, basically. And then the second parameter, D110, is the diameter of the innermost position of the leading edge. And then B2 is basically the height here at the outlet of or at the trailing edge of the impeller. So these are the 3 meridional contour parameters. Then we had some parameters which were related to the blade angle distributions that I introduced before. So we have here 2 parameters for the leading and trailing edge blade angle. So in the upper animation here, you can see the variation of the blade angle at the leading edge. So the 3 curves for hub, mid, and shroud are coupled to each other. So we basically control the hub beta distribution, and the shroud and mid are basically an offset value to that. So you can see they all change simultaneously. And the same thing we do here for the trailing edge blade angle. And yeah, you can see the effects that it has on the blade. Then there is 2 additional parameters for the hub to shroud variation of the leading edge blade angle. So as I told you, we control the blade angle for the mid and shroud contour as an offset to the hub value. And here you can see this amount of the offset changing basically between 0 and the maximum value. So if the offset is 0, then hub, mid, and shroud all have the same leading edge blade angle. Otherwise, there is a certain spread. And the second parameter basically controls where the mid contour is located between these values. And then finally, we have 6 additional parameters that allow us to further fine-tune these blade angle distributions, and basically these control the tangent of these beta distributions at the leading and at the trailing edge. Here they're all changed simultaneously, but it's actually in this case 3 individual parameters to control the tangent angle of this curve for hub, mid, and shroud, and at the leading edge, and the same thing for the trailing edge here. So in total, we have 14 parameters, which allows us a good deal of variation and of creating different impeller types. Of course, we can always add more parameters, but this is what we selected for this study. So let's go to the next step, which is the CFD automation. Of course, now we would like to couple or connect cases to SimScale. Just briefly, before we talk about the actual connection, we want to run CFD for this pump, obviously. So just a few words about the CFD setup. We're running the computations for a full 360-degree impeller. We're using a multiple reference frame or MRF analysis, and that's why we also define here as part of the model the rotating zone, which you see in yellow here in the upper picture. So this is the part that rotates the impeller, and we're running this rotation at a fixed speed of 2,500 runs per minute. And we are using a velocity inlet, and here is an important point. We're computing 3 different flow rates in parallel, so which are 70%, 85%, and 110% of the, so say, designed or optimal flow rate. We're using pressure outlet, fluid is water, obviously, for a heating circulator pump, and a K-epsilon turbulence model. So now let's come to the actual automation. And as you've heard from Kanchan, SimScale is a cloud-based tool. So we're running CFD simulations in the cloud, which from our point of view is a different case than most of our customers are doing. Most of our customers have on-site CFD on their workstation. And here we have a slightly different setup. We have KSBS is a desktop software. It runs on your local workstation, while SimScale runs in the cloud. And to control, as you've seen, SimScale offers this API where you can connect through remotely, and this API is controlled by a Python script. So the Python script basically does everything that is necessary to import the geometry that is coming out of KSBS to the SimScale platform, set up the case by defining boundary condition, mesh settings, solver settings, and so on, everything that you need for the simulation. It will run the computation, or in this case, actually 3 computations for the 3 different flow rates. And then at the end, it will generate the result files and then download the result files to the local workstation again, where they can be imported by KSBS. So, and the connection within KSBS, the connection is done through our so-called software connector, which is a generic interface that we use to connect KSBS to any external simulation computation tool. And in this interface, basically you define all the outputs from KSBS that are sent to the external tool, and all the results that you want to read into KSBS once your computation is finished. So in the upper part, we have the outputs. So this geometry export in the selected format. In this case, we used Parasolid. and then additional input files that are needed for the external tool, which in this case is the Python script I already talked about, and then a batch script to run Python with the arguments that we need. And in the lower part, we have the result files that we want to load into KSES when the computation is finished. And in this case, we have 3 CSV files for head, efficiency, and power, respectively, and with the values at the 3 different flow rates. And then we have an additional text file with the computation runtime that we used for a quick check of convergence. So once we've set up this connection, we can create geometry variants and automatically run them on the SimScale platform. And here's just an example for testing purposes where we just did a variation of one of the parameters that I mentioned. This is the blade angle at the trailing edge of the blades. And then we get in these diagrams, you can see the different results that we get for efficiency, head, and power at the different flow rates and for the different blade exit angles. All right, so now we have the components that we need, geometry, simulation. We have connected the two things together, and then we can go to the optimization, which is the final step. And what we did here is we ran a design of experiments, so a systematic parameter study with the 14 parameters that I introduced before. And we used a Sobol sequence to run this analysis. So this is a yes, kind of a space filling sequence to cover the design space in a homogeneous way. And in total, we ran about 300 impeller simulations. And of course, we ran 300 impeller variants, and each of these variants were simulated with 3 flow rates each. So we have a total of about 900 simulations, which is maybe a bit overkill for the number of parameters that we have here. We could have also done it with less, but we wanted to have a good substantial number. If we would have run all these 900 simulations back to back, sequentially, one after the other, then the cumulative runtime would have been almost 600 hours, so about 25 days, which of course is unthinkable, not really something that you would want to do. And due to the possibility to run things in parallel, so we ran the 3 flow rates for each variance in parallel, and we also run multiple variants in parallel to each other. We could reduce the whole runtime to, as you can see here, 42 point something hours, which basically meant that we started this design study on a Friday evening, and it ran on the weekend, and on Monday all the results were there. Yeah, so we have about 14 computations by average running in parallel, and the computational cost in total is about 3,000 core hours. So from the results of this design of experiments, we can already see some interesting things. Here are the different correlation plots of the 14 parameters plotted against our objectives here. So the head at the 3 flow rates, efficiency at 3 flow rates, and power at 3 flow rates. And we can see that there is actually 3 of the parameters that have a dominant influence on these objectives. One is the inlet diameter of the pump, the number of blades, and the trailing edge blade angle, which is maybe not too surprising if you know something about pump design, but of course also a good validation of the results we have. We can also see that our performance values that we're looking at are well correlated across the 3 flow rates, which basically means, so for example, if we look at power, if we have an impeller that is good has low power at a low flow rate, it also has low power at a high flow rate. But if you look at different objectives to each other, so for example, power plotted against the efficiency, you see there is a certain spread which allows us or gives us certain room for optimization. So the next step with the data of this DOE was to generate the surrogate models. And basically what we did, we have such a result table in KSB where we have all the parameter values and all the objective values, and we exported that table, imported it into an empty project where we wanted to create these surrogate models. And we used a feature within KSB which provides the generation of these surrogate models. It has a few different things you can do. As you can see in the interface here, you can generate the surrogate model based on a certain database, which is this result table that we imported. You can use different ways of generating it. We use a kriging model in this case. There is also other options like a artificial neural network or different polynomial approaches. And then, you can evaluate the model. So you can create a combination of parameter values, which are the geometry parameters in our case, and get the output values. So say the prediction from the surrogate model for our objective values. We have 9 objective values here. The 3 head, efficiency, and power at the 3 flow rates. So we needed to create 9 separate surrogate models for each one of these outputs. And these models that are generated are stored in a file. So once you generate them one time, so to say, they are stored on your PC. It doesn't take long. It takes a few seconds to generate, but still they are there. And then, you can check these surrogate models, which is basically using a so-called leave one out analysis. So you take one of the samples out of the pool and you generate a surrogate model with the rest of the pool, and then you check the prediction for the sample you have taken out and compare it to the actual values. And this gives you and you do that a few times with different samples, and that gives you a measure for the quality of the surrogate model, which is this so-called coefficient of prognosis. And here we got pretty high values of about 95% and above, which of course indicates a very good prediction by the model. And finally we can also visualize individual response surfaces. Of course, the surrogate model is a n-dimensional model, 14 parameters, 9 responses, or 1 response per model, sorry. And here, if we look at, so say, in 2-dimensional hypersurfaces in this model, we can just see, these are 2 selected parameters, and this is the response for the efficiency at the lowest flow rate, for example. And here are the same objective, but other parameters, and you see the responses are obviously quite different based on the influence that the individual parameters have on that objective. All right, so we have the surrogate models in place, and these surrogate models can now provide values for our 9 primary output parameters. So basically we can replace the CFD computation with the prediction from the surrogate model, and we can take these values and we plotted them in diagrams for the head efficiency and power curve. And as a derived value, we also computed the slope of the curve, which is something that we might want to use for the optimization because it describes also some properties of the curves that we're looking at. We also included in the surrogate model project setup in KSB a very simplified geometry model with just a hub camber line that gives us some additional outputs about the geometry, the trailing edge blade angle, and the total wrap angle of the blade, which is things that a pump designer is typically interested in, and gives a good idea of how the pump or the impeller would look like. And now, with that set up, we are able to run optimizations with these surrogate models. You can see here an example. Again, this is just a DOE, a systematic study where we change the geometry. You can see how the blade changes in the bottom, and then these curves that were with the values that come out of the surrogate model in comparison to the baseline curves, which are the ones in dark red here. So as Tony, coming back a little bit to what Tony introduced at the beginning, our final goal is of course to be able to simply optimize the impeller for a minimal energy efficiency index. But as Tony has explained, there are additional challenges to derive the necessary data to compute this energy efficiency data from the pure CFD results we have, right? There was this kind of difference between calculated and measured curves. We also run the computations at a fixed RPM, and we don't have the curves for different RPMs. So there is different things that need to be done in order to derive this final EEI value from our CFD results. And this is still something we're working on. We're still a work in progress. But of course, we wanted to test our workflow and the surrogate models that we've created. So we used some assumptions to start with, and the assumptions were we would like to increase the efficiency of the impeller at the lowest flow rate. As you remember, the EEI calculation has a weighting for the different flow rates, and you can see the lower flow rates are disproportionately weighted in this average power consumption. So the lowest flow rates are important, and we would like to increase the efficiency there. And also we would like to try to reduce the slope of the power curve, so to reduce the power requirements at high flow rates, and basically prevent this kind of breakdown of head that Tony also showed if we have a motor that hasn't enough power. And this is the assumption without having the full EEI computation implemented yet. This should lead to a lower energy efficiency index. So what we did here was we took our surrogate models, and then we ran an optimization run using a genetic algorithm here with 10 generations, 32 designs per generation. It's obviously relatively quick, so we have a 30-minute runtime in total for these 320 designs, so about 10 designs per minute are evaluated. You can see here the different generations. And what we get as a result is a more or less well-formed Pareto frontier with different Pareto optimal designs that we can choose from. So this is the diagram here. Efficiency at the lowest flow rate plotted against the slope of the power curve. And here are the designs that are performing well with respect to these two objectives. So we selected one of these designs as a result, and you can see it fulfills the requirements that we set. There is a slight reduction in head, which is acceptable. And you can see it with the efficiency curve. We have a significant increase of efficiency at the lowest flow rate, as well as an increase also for the other flow rates. and we have a lower power requirement. So the curve itself is shifted lower, but it also has a slightly lower slope of the curve. So the power consumption doesn't rise as quickly with our higher flow rates. The design, if we look at it in terms of the geometry, has a smaller trailing edge blade angle. So here you see the baseline design had 36 degrees, and here we have about 28 degrees trailing edge angle, and we have a larger rep of the blade. So we had something like 80 degrees, and now we have about 120 degrees rep, and a lower number of blades. The initial design, the baseline had 7 blades, and now we have 6 blades. So as a final step, we have basically our set of parameters for the optimized impeller variant, and now we can transform it back to a geometry. And to do that, we used again our connector interface here, and in this case we just connected cases to cases to launch a second cases instance in batch mode, where we send the parameter values to, and then we generate the actual geometry using a batch script, quite simply, and then we have our optimized geometry. Okay, this covers the workflow we have worked on. And now let's come to some conclusions. So using the SimScale CFD analysis in the cloud was instrumental for this project because we can run a very high number of variants with multiple operating points in a very short time using the parallelization possibilities. Based on these results, we can create these surrogate models that, so to say, persistently store the generated database and can then be used to efficiently and very quickly predict the performance of a new impeller with a satisfactory degree of precision. With these surrogate models, we are able to run a very quick and fast, as was, so to say, the requirement at the beginning, optimization of the impeller geometry using custom requirements. And with these different components that we put together, we achieved a first iteration of this hydraulic part of the tool chain for the minimization of the pump's energy efficiency index. Of course, there is still some work open, as I mentioned, to really finally be able to optimize for EEI, but I think this work will be continued. Thank you very much. I would like to thank everyone who worked on this project with us, including a few people mentioned here that were, so to say, behind the scenes that are not showing up in the webinar. And thank you very much for your attention.
Thank you. Thank you, Mattia, for a wonderful presentation and a very detailed description of the workflow. And I would also like to thank our teams, as you mentioned, Johannes and Omar, who worked behind the scenes to make this all possible. And they are here as panelists in the webinar to help us answer questions, which is what we will be doing. We have a few minutes to take a few questions. I encourage everyone to please type in using the chat option. And so, Mattia, I have one question for you, which asks, can we also plot self-organizing maps?
That's a good question that I might be able to answer you if I would know exactly. So I've heard of self-organizing map. I've seen something, but to be honest, I don't have enough knowledge about the exact meaning of that. I think it's probably possible, and that's not something we have worked on so far or looked at. I mean, I'm open to trying these things, but I cannot tell you for sure.
Thank you, Mattia, and sure, something for us to get back to the attendee with the answer. And another question coming in is, does this simulation include cavitation effects? And I can probably answer that, that this simulation particularly does not include any cavitation effects. This was a straightforward steady state simulation. We're using the MRF method. But in general, in SimScale, you can include cavitation for pump or hydraulic equipment simulations.
Yeah, and it was, I think, a conscious decision. Tony um, also told us that we can neglect cavitation for this case. Maybe Tony, you have 2 words to say about that.
Yeah, normally cavitation is no issue for this kind of pump, so we neglect it. Of course,
Right.
we have to recheck this, with a newly designed impeller. Yeah, this is clear.
Correct.
Yeah, we have to recheck,
Okay.
but normally cavitation should be no issue.
Right. Ed, one other question on the simulation side is, does the 3+ core hour per design include meshing and convergence? Yes, it does. What is the size of the mesh and the pump, and how many iterations were run? So I think, Omar, I will hand that question to you to give us a little bit more details on the simulation stats per simulation.
Yeah, absolutely. So the 3+ core hours does include the entire workflow from meshing to convergence. The mesh size is very dependent on the actual pump design, since there's an automated Cartesian mesher occurring in the background for each setup for each geometry. So looking at just the baseline geometry, the baseline pump design, it was around 850,000 cells within the fluid domain. So that gives you a rough idea of what to expect in terms, maybe a 10 to 15% variation up and down for all the geometries combined. So that's the rough variation there. In terms of the size of the pump, it's actually around, I guess it depends on the direction, but around 7.5 centimeters roughly in terms of the fluid domain. But the overall assembly is probably larger. If Tony can add on that.
Thank you. Thank you, Omar. And we have just a couple of more minutes for some final questions before we will have to close the meeting room. Does KSB run on multiple cores?
Yes, it does. It does. It is, however, not necessarily a big deal, because I mean, KSB doesn't run a lot of very heavy computations. If you run optimizations with CFD, for example, then of course the computational cost and time that KSB takes is negligible in comparison to the CFD computations.
I see.
It might become a bit more interesting if you run an optimization with these surrogate models, because you have, of course, a very quick computation of the results, and then most of the time is spent generating variance and running the algorithm. So yeah, but it is parallelized and it runs on multiple cores.
And I have just time for one final question, which is directed at SimScale. Can Fusion 360 be used as the CAD system with SimScale? Yes, we do support all popular CAD formats from different design tools. And as long as there is an API-based workflow that is possible, we have an open API, and if the same is possible on the other end, we can do a similar integration with Fusion 360 as well. Omar, if you want to add anything to that.
No, that's a good way to cover it. Really, just most major CAD packages are supported. We have, so you can look more on the website for your specific niche CAD, but the generic file formats cover most of that as well.
So I'm afraid we do not have time anymore for any further questions. I really want to thank you all for joining us today, and thank you, Mattia, thank you, Tony, Johannes, all of you for working together on this wonderful project, and hopefully we can continue the good work. Thank you everyone for joining. Have a very good day ahead.
Thank you from my side as well.
Thank you.
Bye bye.